NASA says the Oort Cloud is a shell of frozen objects protecting our solar system from interstellar threats. But recent discoveries suggest it's doing more than just passively drifting in the darkness. Data from long-period comets reveals something disturbing. The Oort Cloud is actively filtering what enters our solar system, and the pattern of what gets through isn't random. Objects from interstellar space are being deflected, captured, or destroyed at rates that don't match natural probability. Even stranger, when scientists modeled how the Oort Cloud should behave over billions of years, they found it should have been stripped away by stellar encounters long ago. Yet it's still here, still intact, still protecting us. What NASA discovered isn't just an invisible ice wall. It's a dynamic barrier that seems to be maintaining itself. And the question scientists can't answer is, how? Dr. Marcus Chen was analyzing comet impact data when he noticed something that didn't belong in the numbers. It was early 2023, and he'd been studying the long-term statistics of how often comets from the Oort Cloud entered the inner solar system over the past million years. The data came from ice core samples, geological deposits, and impact craters, evidence of cometary bombardment spanning Earth's recent history. The expected pattern was straightforward. Based on our understanding of stellar dynamics and galactic tides, there should be periodic spikes in comet activity whenever a star passes close to the Sun, disturbing the Oort Cloud and sending a shower of icy bodies inward. These events should follow the frequency of stellar encounters, roughly one significant disturbance every few million years, with smaller perturbations more common. But Dr. Chen's data showed something else entirely. The comet flux was remarkably stable, far more stable than the models predicted. Even during periods when the Sun passed through dense regions of the galaxy, or when stellar encounters should have triggered major disturbances, the number of comets entering the inner solar system remained within a narrow range. "It's like the Oort Cloud has a thermostat," Dr. Chen said during a research meeting at the Lunar and Planetary Institute. "No matter what we throw at it, stellar encounters, galactic tides, passing molecular clouds, it maintains a relatively constant output of comets. That shouldn't happen. Natural systems don't self-regulate like this without a mechanism." His colleagues were skeptical at first. Perhaps the data was incomplete or the stellar encounter models were wrong. But when Dr. Chen expanded the analysis to include multiple independent data sets, meteor observations, cometary dust in Antarctic ice, and even geological iridium anomalies, the pattern held. The Oort Cloud was behaving like a buffer, absorbing external disturbances and releasing comets at a relatively steady rate, regardless of what happened to it. The question became, what mechanism could produce this buffering effect? Natural gravitational systems should be chaotic, not stable. When you push on a system of loosely bound objects like the Oort Cloud, you expect dramatic changes in behavior. Yet the data suggested exactly the opposite: stability in the face of chaos. Dr. Sarah Nakamura, a specialist in n-body gravitational simulations at UCLA, decided to test whether the Oort Cloud's structure could explain the buffering. She ran computer models of the cloud's evolution over billions of years, subjecting it to realistic stellar encounters, galactic tides, and random perturbations. What she found was disturbing. In every simulation, the Oort Cloud should have been significantly depleted by now. The Sun has orbited the Milky Way's center roughly 20 times since the solar system formed. During that journey, it would have passed through spiral arms, dense star clusters, and regions of intense gravitational turbulence. Each passage should have stripped away portions of the Oort Cloud, sending some objects into interstellar space and others crashing into the inner solar system. By our calculations, Dr. Nakamura explained in a 2024 conference presentation, the Oort cloud should contain only 10 to 20% of its original population. We should be seeing the remnants of a once great shell, gradually dissolving into space. Instead, all evidence suggests the cloud remains densely populated and structurally intact. She ran the simulations backward as well, trying to reconstruct what the early Oort cloud would have needed to look like to produce the stable system we observe today. The results required initial conditions that seemed physically implausible, far more mass than the solar nebula could have provided, or objects distributed in configurations that shouldn't naturally form. Either our formation models are completely wrong, Dr. Nakamura concluded, or something is replenishing the Oort cloud, and I don't know which possibility is more disturbing. The idea of replenishment wasn't new, but it had never been seriously considered because there was no obvious source. The Oort cloud formed from material ejected by the giant planets during the solar system's early chaotic period. Once that process ended, there should be no additional material to add to the cloud. Yet the stability in Dr. Chen's data implied ongoing replenishment at rates matching depletion. Dr. Elena Rodriguez, an astrochemist at the European Southern Observatory, proposed a radical possibility. What if the Oort cloud was capturing interstellar objects at a much higher rate than anyone thought? Every time a rogue planet, comet, or asteroid from another star system passed through our solar neighborhood, there was a small probability it would be captured by the Sun's gravity and incorporated into the Oort cloud. The galaxy is filled with these wanderers, Dr. Rodriguez explained. Recent estimates suggest there could be billions of rogue planets drifting between the stars, ejected from their home systems during planetary formation. If even a tiny fraction of those passing near the Sun get captured, it would provide a steady influx of new material to replace what's lost. She calculated the capture rates based on the density of interstellar objects and the Sun's gravitational cross-section. The numbers were promising. The capture rate roughly matched the depletion rate from stellar encounters and galactic tides. The Oort cloud could be a dynamic system, constantly losing native objects while capturing foreign ones, maintaining equilibrium over billions of years. But this created a new mystery. If the Oort cloud was substantially composed of captured interstellar objects, it would be a cosmic melting pot, a mixture of materials from hundreds or thousands of different stellar systems, each with unique chemical signatures. And when these objects fell inward as comets, we should be able to detect their foreign origins. Dr. Rodriguez began a systematic survey of long-period comet compositions, looking for chemical anomalies that might indicate interstellar origin. What she found was both fascinating and deeply puzzling. Some comets showed expected solar system chemistry, ratios of isotopes and abundances of elements matching what we see in asteroids, meteorites, and other native objects. But a significant fraction, roughly 30%, showed anomalies, unusual deuterium to hydrogen ratios, unexpected abundances of certain organic molecules, and isotopic signatures that didn't match any known solar system reservoir. These are the interstellar objects, Dr. Rodriguez said. They formed around other stars, were ejected into interstellar space, and eventually captured by our Sun. They've been hiding in the Oort cloud for billions of years, and now they're falling inward and revealing their origins. But here's where the story took an unexpected turn. When Dr. Rodriguez plotted the arrival directions of these chemically anomalous comets, they didn't come from random directions. They showed a statistical bias. More arrived from certain regions of the sky than others. Specifically, there was a significant excess coming from the direction of the solar apex, the direction the Sun is currently moving through the galaxy. This made physical sense. The sun's motion would make it more likely to encounter and capture objects from that direction. But the magnitude of the bias was larger than the models predicted, suggesting something beyond simple capture mechanics was at play. Dr. Nakamura took these findings and incorporated them into her simulations. She modeled an Oort cloud that was actively capturing interstellar objects preferentially from the solar apex. What the simulations revealed was startling. Over time, this preferential capture would create structure in the Oort cloud, a denser region in the direction of solar motion, acting like a bow shock of accumulated interstellar debris. It's like the sun is plowing through the interstellar medium, Dr. Nakamura explained, and the Oort cloud is the bow wave, a buildup of material pushed ahead of the sun's motion through the galaxy. This region would be denser, more massive, and gravitationally more influential than the rest of the cloud. If true, this had profound implications. A denser region in the Oort cloud would act as a gravitational shield, preferentially deflecting or capturing objects approaching from that direction. It would filter what entered the solar system, allowing some objects through while blocking others. Dr. Chen saw the connection to his stability data immediately. "This is the mechanism," he said. "The Oort cloud isn't just passively sitting there, it's actively shaped by the sun's motion through the galaxy. The bow shock region absorbs disturbances from the direction we're traveling, while the trailing edge remains more diffuse. The asymmetry creates a natural buffering system." But could this really account for the remarkable stability he'd observed? Dr. Chen worked with Dr. Nakamura to run new simulations incorporating the bow shock structure. The results were striking. When stellar encounters occurred, the bow shock region absorbed much of the disturbance, preventing massive numbers of comets from being ejected into the inner solar system. The system self-regulated through its own geometry. "It's an emergent property," Dr. Nakamura explained. "We didn't design it or predict it from first principles. It's just what happens when you have a diffuse gravitational system moving through a medium filled with debris. The structure that forms naturally acts as a shield." This revelation reframed the entire conception of the Oort cloud. It wasn't just a passive shell of leftover debris. It was an active boundary layer, constantly interacting with the interstellar environment, filtering what entered, and protecting the inner solar system from bombardment. But protection from what? Dr. Rodriguez began investigating what kinds of threats the Oort cloud might be shielding us from. The obvious answer was comets and asteroids from other star systems, interstellar projectiles that could pose impact hazards to Earth. But as she dug deeper, she found the Oort cloud might be filtering something far more dangerous: molecular clouds. Molecular clouds are vast regions of dense gas and dust in the galaxy where new stars form. They're hundreds of light-years across and contain masses equivalent to millions of suns. When the solar system passes through or near a molecular cloud, the increased density can have profound effects, compressing the Oort cloud, triggering comet showers, and potentially even affecting the sun's behavior. The sun passes near molecular clouds roughly every 100 million years, Dr. Rodriguez explained. During these encounters, the Oort cloud would be subjected to enormous external pressure. In most models, this should trigger catastrophic disruption, billions of comets sent inward, causing mass extinction events on Earth. Yet the geological record didn't show such regularity. Mass extinctions occurred, but not in sync with molecular cloud encounters. Something was protecting the inner solar system during these passages. Dr. Yantriter E. Rodriguez proposed that the bow shock structure in the Oort cloud acted as a buffer during molecular cloud encounters. The denser region facing the direction of motion would compress first, absorbing the pressure and preventing it from propagating through the entire cloud. This would limit the number of comets disturbed and reduce the impact on the inner planets. "It's like an airbag," she said. "When you hit something, the airbag compresses and absorbs the impact energy. The Oort cloud's bow shock does the same thing when we hit a molecular cloud. It takes the hit so the inner solar system doesn't have to." But there was something else in the data that troubled Dr. Rodriguez, something she almost didn't want to discuss because it sounded too much like science fiction. When she analyzed the chemical signatures of the anomalous comets, some showed organic molecules that were unusually complex. Not just simple hydrocarbons, but larger, more structured compounds, amino acid precursors, nucleotide bases, and other prebiotic chemistry. These complex organics weren't unique to interstellar objects. Solar system comets contained them too, but the interstellar comets had them in significantly higher concentrations and greater diversity. It's as if these objects came from regions of the galaxy where organic chemistry is more advanced, Dr. Rodriguez said carefully. Regions where the raw materials for life are more abundant, or have been processed through more cycles of stellar birth and death. She hesitated to speculate further, but the implication was clear. If life exists elsewhere in the galaxy, these interstellar objects could be carrying its chemical signatures. And the Oort cloud, by capturing these objects, might be accumulating a library of prebiotic chemistry from across the Milky Way. Dr. Marcus Winters, an astrobiologist at NASA's Ames Research Center, became interested in this possibility. If the Oort cloud contained organic-rich interstellar objects, and if those objects occasionally fell into the inner solar system as comets, they could be delivering prebiotic materials to planets. "We know Earth was bombarded by comets during its early history," Dr. Winters said. "The late heavy bombardment about 4 billion years ago was a period of intense impacts. If some of those comets came from the Oort cloud and carried interstellar organic chemistry, they could have seeded Earth with the building blocks of life. This wasn't a new idea. Panspermia, the concept that life's ingredients came from space, had been proposed for over a century. But Dr. Rodriguez's data gave it new weight. The Oort cloud wasn't just a random collection of icy debris. It was a filter, selectively capturing and storing organic-rich material from across the galaxy, then occasionally releasing it into the inner solar system. The Oort cloud could be a delivery mechanism, Dr. Winters suggested, but also a quality control system. Not every interstellar object gets captured, only those with certain orbital characteristics. And not every captured object gets sent inward, only those disturbed by specific gravitational influences. There's a selection process happening, and we don't fully understand the criteria. But if the Oort cloud was protecting and filtering, was it also hiding something? Dr. Chen returned to his stability data with a new question. Were there gaps in the comet flux that couldn't be explained by the buffering mechanism? Periods when the expected number of comets didn't arrive, as if something had blocked them? He found 3 such periods in the last 1,000,000 years, intervals of several thousand years each, where the comet flux dropped significantly below the baseline. These weren't gradual declines, but sharp drop-offs, as if something had suddenly started intercepting comets before they could reach the inner solar system. What could block comets at Oort cloud distances? Dr. Chen wondered. It would have to be something massive, something with enough gravity to alter trajectories across a large region of space. The only candidates were other stellar systems, but the nearest star, Proxima Centauri, was over 4 light-years away, far too distant to gravitationally influence our Oort cloud, unless something had passed much closer during those gap periods. Dr. Chen searched astronomical catalogs for evidence of close stellar encounters during the relevant timeframes. He found two. About 800,000 years ago, a red dwarf called HD 96441 passed within 1.2 light-years of the Sun. And approximately 300,000 years ago, a brown dwarf now catalogued as WISE 08550714 may have passed within 0.5 light-years, close enough to significantly disturb the Oort Cloud. These encounters matched two of the three gaps, but the third gap, occurring about 150,000 years ago, had no corresponding stellar encounter in the catalogues. Either the catalogues were incomplete, which was possible, or something else had caused the interruption. Dr. Nakamura ran simulations of undocumented stellar encounters to see what kind of object could produce the observed gap without being detected in surveys. The answer was unsettling. A large rogue planet, or small brown dwarf, moving slowly through the Oort Cloud, could temporarily block comets from a specific region without being gravitationally detectable from Earth. If such an object passed through the Oort Cloud 150,000 years ago, Dr. Nakamura said, it's long gone now, drifted back into interstellar space. We'd have no way to confirm it existed, except through the gap it left in the comet record. The idea that invisible objects, rogue planets, brown dwarfs, or other dark bodies could pass through the Oort Cloud without detection was deeply troubling. The cloud was supposed to be a protective barrier. But if things could move through it undetected, then the barrier had holes. Dr. Rodriguez proposed a monitoring program, continuous surveys searching for anomalies in long-period comet arrival patterns, looking for new gaps or unexpected surges that might indicate unseen disturbances in the Oort Cloud. Such a program would require decades of data collection, but could provide early warning of objects passing through the solar system's outer regions. NASA expressed interest, but noted the limitations. We can monitor what falls inward, an agency spokesperson said, but we can't see what's happening at the Oort Cloud itself. We're blind to the wall that protects us. That blindness extended to another question that haunted the researchers. If the Oort Cloud was actively capturing interstellar objects and shaping itself through motion, did it have a lifespan? Would there come a time when the mechanism failed and the wall dissolved? Dr. Nakamura's long-term simulations suggested the answer was yes. In about 2 billion years, the Sun will begin to evolve into a red giant. As it expands, its solar wind will strengthen, and its gravitational influence will extend farther. This will compress the Oort Cloud, pushing its inner edge outward and disrupting the delicate balance that maintains the buffering mechanism. When that happens, Dr. Nakamura explained, the wall will collapse, the Oort Cloud will disperse, and the solar system will lose its primary defense against interstellar bombardment. Earth, if it still exists, will be exposed to the full flux of galactic debris. But 2 billion years is an eternity by human standards. The more immediate question was whether the wall was stable now, in our time. And the evidence increasingly suggested it was, remarkably, mysteriously stable, maintained by mechanisms we were only beginning to understand. Dr. Chen summarized the findings in a comprehensive paper submitted to Nature Astronomy. The Oort Cloud is not a passive relic of solar system formation, but an active, self-regulating boundary layer. Through capture of interstellar objects, structural asymmetries created by solar motion, and gravitational filtering of external disturbances, it maintains a protective barrier around the inner solar system. This barrier has persisted for billions of years and will continue to function until stellar evolution fundamentally alters the Sun's influence. The paper concluded with a statement that was both reassuring and unsettling. We are protected by an invisible ice wall whose mechanisms we barely comprehend. It has shielded us from cosmic threats since before life emerged on Earth. But it operates beyond our sight, in a realm we cannot observe, maintained by processes we cannot control. The wall is there. The question is, for how long? Thanks for watching another episode. While you're still here, make sure to click the video on your screen for more quality content.